Oh. Oh, thanks, so hopefully everyone in the room can hear me. Yeah, hopefully everyone online can hear me. I can't see anything on my screen anymore. We'll see other folks.
Hey, Andre, we can't see your screen.
I can't see my screen.
You can't see your screen.
Michael can see my screen in Australia.
I can see your screen.
Oh, yes, sorry, I can't.
Good start.
Good work, team.
Good start.
That's the word. That's what we want. Lots of feedback. Okay. So we're recording. Yeah, we're recording. So just remember, we're recording. And if you log into the Zoom room that I emailed around, you're going to see what's being recorded. There's a camera pointing to me. It will stay pointing here. It won't follow me. And we share the screen. So you want to talk in, try and log into Zoom to share the screen. Wi-Fi is up there, waiting to go resolve with the password, waiting to resolve with the architects that we get that. Okay, so welcome. After a year break last year for some reason, we're back. The 2021 International CellML Workshop. And of course, today's the day the biggest rating bubble opened, and yet the team in Melbourne didn't come. So we're very fortunate to have a number of them online with us today, and coming up in a few days, we'll see a few more people from overseas able to join us, as well as from those over the harbour here. So yeah, so when you're presenting, be good to use Zoom to make sure everyone can see your slides, and we may just leave my computer here plugged into the projector to use that. We'll see how we go. We're a bit out of practice doing these things. So that's not working. There we go. So of course, we always start by thanking our sponsors, and this year we're very grateful to ABI, who have enabled us to come out here to this lovely location and have this workshop. And of course, I don't do any work. So a big thanks to Dana for pulling this together, that she got us all here. Missing one person who's supposed to be on the wasn't. So thanks, Dana. Well done. We're here. The morning tea was good, but they ran out of coffee. Then also thanks to the other organisers of this. We've done Kate, Hugh, Alan, and Nan, who of course picked this week to be on holiday. So he's not here, so we can talk about lots and watch the recordings. And because, as always, we're very, very unorganized, you might have seen a program come out late last week to show you what we're talking about. A huge thanks to everyone for actually showing up, both in person and online. We weren't really sure if we ever had anyone who left it a bit later than usual. So thanks to everyone for coming. We can't read that, but the PDF is there on the website showing the program for this week, for these 2 days. We're running a little bit late, but we'll soon be jumping into bond graphs with a few talks. Then after lunch, we have some lightning talks. Then this afternoon, we'll talk more about reproducibility and model curation. Let's see how that goes. Tonight we have dinner. And tomorrow, if there's time, talk a little bit about the Spark Fair Codathon that some of you may have seen. And then we have Peter going to talk to us about the 12 labors, and a team from Chicago talking about their work to get CellML into Julia. After lunch tomorrow, we're going to try some tutorials. We may have an installable with CellML by then, and we'll see how that goes. We've never done that at one of these before, so we'll see. And if there's time after that, we might also have a tutorial on this annotation library that some of us have been working on. And then round out the workshop with some talk about PMR and physics. So this is the list of lightning talks we have. What you'll notice is if people don't volunteer to talk, I fill up the time. So if you don't want me to talk more, please volunteer your name to give a lightning talk. You can definitely add more. Or if you want to talk on any of the topics, feel free to volunteer and certainly halfway to the schedule. These are the ones we have. Probably use this order, maybe, or randomly change it. So one thing you may notice is this year there's no session introducing the nominees standing for the CellML editorial board. And what we see is the current editors, as far as I can remember sitting on the ferry. We have Hugh, Gary, Jesus, Jesus, I don't know, I think you pronounce it as Jesus, Max and Paul. And some of them have been on the board for a while now. With last year's cancellation of the workshop, the editorial board all agreed to extend another year of their terms. But, you know, essentially COVID broke the election cycle. So there's a period now we're trying to work out exactly what to do. But some people have left, some people might want to step down, and we need to sort of start the clock again in terms of people's terms. So I think there might be a case of looking at electing a few people potentially for not complete 3-year terms. So 15, look out for the call for nominations that will probably come out soon. But I think one of the important things is that now that we have CellML 2 and with CellML almost ready, we're in a place now where we can be a lot more responsive and do incremental improvements to the spec. So hopefully the editorial board will get a lot more active and interested into partake. So we'll see how that goes. But in terms of responsiveness and incremental improvements, it might be worth noting the 17 years between 1.1 and 2.0. So anything less than 17 years is a good thing. And then we'll see how we go. But yeah, and essentially that 17 years is pretty much when the first CellML workshop was. Back in 2006. Which is probably maybe good, you know. And so for those that have indicated they're keen for dinner, if you haven't indicated or changed your mind, feel free to let us know. I'm sure Nima can sort it out. And so he's arranged for us to go to a place called Oyster and Shop in Providence. It's a short walk from the ferry terminal. So basically hang around when you get off the ferry, or if you're online and coming along, meet us down at the ferry or just at the restaurant. And we're there at 7 o'clock tonight. Of course, when you look back at the previous workshop, we actually put our Zoom link on the website. Can you believe that? Nowadays, of course, you never do that. We can get some interest in people attending the Zoom meetings. So please don't share the link, or we'll have to reset everything. As I said, it's good to connect to Zoom, share your screen, to make sure everyone can see what's going on. I just realized I have no idea what we're going to do when remote people present, but I'm basically going to wait for that. If you do join the Zoom and you're in the room, just don't join the audio. Just close that box when it comes up. Don't even join at all. Or if you do, make sure your microphone and speakers are both muted. Otherwise, you'll get lots of feedback. It's not fun. And we are recording the sessions. If things go well, we'll put them up online somewhere for later. I think the ones from 2 years ago are almost ready to put online, maybe. But don't forget it's recorded. Camera's pointed from there to here, so anything in there is getting picked up, and it's mostly picking up the sound. So just be aware of what's happening. Okay, so I've got anything else. That looks like it. So that's us started. Now I can find my mouse. We can get into the regularly scheduled program. Almost on time. If I remember correctly. And very carefully. Yeah, so first we're going to have, so we're essentially now going into a session on monographs. Mostly because this is the best time to have it while everyone's fresh and awake. And Michael from Melbourne is going to start us off talking about analyzing and simulating energy-based models in biology using long-graph tools. And I'm going to try and put something on the projector. There we go.
Wait a second.
Okay, Michael.
I'm just sharing my screen. Okay, can you see it now?
Yes, we can see it.
Is that online or at the venue?
We in the room can see it.
Okay, great. All right, thanks, Andre. So for this talk, I'm going to introduce to you a software tool that you can use to construct bond graph models and discuss how it might be useful for modeling biology. But before we get into that, I just wanted to make an acknowledgement. So as many of you will probably know, Bond Graph Tools, this software package, was initiated and largely developed by Pete Cutmore, who was a former postdoc in our lab. And if you're interested in the code, you can find it on GitHub. And the material in this talk is also up on a bioRxiv preprint. Okay, so first of all, I thought I might just quickly introduce bond graphs for those who aren't totally familiar. So the basic idea of bond graph modeling is that they're a graphical and nice representation for physical systems. So for example, if you have an electrical circuit, in this case, an RLC circuit, you can represent it by this bond graph here. So for example, this resistor's mapping to this R component. So for each component, you have an equivalent bond graph component. One of the nice things about bond graphs is that they're a general representation. So alternatively, if you had a chemical reaction, which happens to be a bit more relevant for biological systems, you can also represent that as a bond graph. Then another nice thing about bond graphs is then each of these components has its own set of differential equations. Sorry, not differential equation, its own equation. So for example, this R component or resistor, it's got an Ohm's law. And similarly for your chemical components, they've got nonlinear equations, a bit more complicated, but they're still equations. So from all of these equations, what you can do is you can algorithmically derive a set of differential equations for these systems. So for the electrical circuit, you've got a second order differential equation, as you'd expect. And for the chemical reaction, you've also got a set of differential equations. Okay, so then why use bond graphs? Well, first of all, they're energy-based. So if we go back to the previous slide, each of these bonds carries with it some potential or flows. So in electrical circuits, you've got voltage and current. In chemical reactions, you've got chemical potential and flow rate. And their product gives you power. So you're explicitly accounting for energy, which is something you can use to help make your models more likely to be consistent with the laws of physics. As we discussed before, it's also graphical. So it's a visual representation, but also nice is the fact that you can explicitly derive equations from these graphical representations. You can do it algorithmically. And then these bond graphs are modular, so you can take components and then build models by connecting up together. So you're dealing with models on the level of components and connections rather than equations which are a bit more error prone. And you can also connect up your modules, your components together into modules that you can then copy and reuse across multiple parts of a larger model, which can be helpful in certain cases. But what we found when we were looking at existing software implementations of bond graphs is that there were certain limitations when we tried to use that for biology. So as an example of this, on this slide, we have a screenshot of one of these kinds of modeling softwares, which is 20sim. And as you can see, it's largely graphical and it's also proprietary. And that's good for certain applications in engineering, but it's also quite troublesome in some cases when we're trying to model biology. So one issue is that it's proprietary, which means you're not free to openly share your models. And also related to that is that if there's some feature in the software that you want but isn't there, it's quite difficult to add that feature in because it's in a proprietary environment. And then finally, since this is embedded within a graphical user interface, it can be quite difficult to automate certain tasks. So for example, if you had one module that you wanted to create multiple times with minor changes, for example, that's quite difficult to do in a graphical user interface. Okay, so when we were developing bond graph tools, we had these kinds of limitations in mind, and we wanted to overcome some of these. So in short, bond graph tools is a Python package for creating, analyzing, and simulating bond graph models. And it was developed with a few principles in mind. So first of all, it's open source, so it's freely available online for you to download and use. And rather than being embedded within a GUI, it's embedded in a scripting environment. So that allows you to automate tasks like copying across multiple parts of a model that happen to be similar. And then finally, since it's in Python, it's extensible, so you can use it in conjunction with lots of other Python packages. So these are things like symbolic manipulation or plotting functions. And if there happens to be some functionality that's not inherently available within bond graph tools, so maybe something like parameter fitting, it's relatively simple to add that yourself by writing your own code. Okay, so having just introduced bond graph tools, let's just discuss some basic functionality. And to do this, I might as well just use a simple system. So this is a simple chemical reaction, which you can describe using this bond graph on the right. And if you wanted to define this model in bond graph tools, you'd use a bit of code like this. So let's just go through that. So obviously the first thing you do is you import the package. And then you have to tell Python that you're making a new bond graph model. So that's this new function in bond graph tools. And then within that model, you see we've got 3 components, 2 species and 1 reaction. So that's what's being defined in these next few lines. So here we're defining a new component for each species and the reaction. And then we use the add function to add it to the model. And you'll also notice that for each of these components, we can define their parameters as well. So now we've got our components. The final thing left to do is to connect these components together. So what we've done is we've connected the species A to the reaction, and we've connected the reaction to the species B. I'm sorry, is there anything wrong? I'm just going to go ahead. Okay, so now we've defined our model, and what we can do now is bond graph tools gives us some functions that'll help us to, well, let's give us some functions that'll allow us to do our analysis. So one thing we can do is we can draw the model. So that just gives us a graphical representation of the model again. It works quite well for debugging simple systems, although if you try and draw a really complicated model, things can get quite messy. So the layout's something we'll need to work on in the future. You can also use the constitutive relations method to output the differential equations of the model. So you can get the differential equations out. In this case, it's an ODE. And so BondGraph Tools has it's got some functions that automatically allow it to reduce the order of your equations. And then finally, you can also, well, if you input a set of initial conditions and a time span, you can simulate your model and plot the results. So that's great. So then if we're going to look at systems biology, that's where we expect this scripting environment to be quite useful, right? Because lots of these models can get quite complicated. So you want to make use of automation wherever possible. So to illustrate how this might be the case, let's use a model of the phosphorylation of a protein at 4 sites, just to explain how it might be useful. So what's happening here is you've got a protein and it's got 4 sites where you can have a phosphorylation. So we have one enzyme that adds phosphoryl groups or phosphate groups to the protein, and then another enzyme that removes it. And if you look at the full biochemical reaction network of the system, it can look quite complicated. And if you draw a bond graph of it, it's going to look even worse. So ideally, there's a way of specifying these kinds of models without having to go to the level of components and connections. And thankfully, since BondGraph's a scripting tool, you can actually write your own functions that'll allow you to do that kind of stuff. So actually, BondGraph Tools gives you a different kinds of constructor for making bond graphs of biochemical networks. So that's this reaction network class, which you can define up here. And essentially what you can do is you can then write down strings for your reactions, which essentially defines your reactions. And you can also define certain species that you want to hold at constant concentrations. And then finally, you've got a function that lets you convert that reaction network into a bond graph. So in this case, you can specify your model not by components and connections, but by reactions. So having defined that model, you can now obviously draw the bond graph of it, or you can derive its equations. I won't actually show you the equations because they're quite complicated, but here is a simulation of the model. And these are actually multiple simulations where we're starting the model from different initial conditions. And you can see it goes to 3 distinct steady states, which has been observed in these kinds of systems before. So that's good. Okay, but then you can also take this idea of automation even further, right? Because before we were looking at a model of phosphorylation at 4 sites, but in general, proteins don't necessarily have the same number of sites for phosphorylation. Some might have as few as 1, some might have as many as 50. And obviously you need different models for them, but really they share the same kinds of structures. So ideally you don't want to have to write new code every time there's a new phosphorylation model with a slightly different number of sites. Thankfully, BondGraph Tools, since it's in Python, gives you a way of automating these kinds of processes so that you can actually create general kinds of models in a certain class. So for example, if we have this, we can define some sort of multi-site function, which outputs a model of phosphorylation with a general number of phosphorylation sites. And obviously there's a bit of code missing because it can get a bit long. But having defined this function, if you want a model with 50 phosphorylation sites, which is quite complex to do manually, you can just call on this function and then input in 50 phosphorylation sites, and it gives you the full model. regardless, despite the fact that it's really complicated. So that's nice. Okay, so where to from now? So BondGraph Tools is being used in a few current projects. So one thing we're looking at is annotating models. So as a lot of you might know, bond graphs, their components are related to the physics of the system. So that can be quite useful when you're trying to annotate these kinds of models, because each component is actually linked to some sort of physical component or process. And we're also looking at using these kinds of annotations to automate the process of composing models together. So getting two separate models and making them talk together. And Nilufer at the ABI, who's actually going to be talking in this session, is working on this. We're also planning to use BondGraph tools for whole cell modeling. So these are models of cells which attempt to account for every single biomolecule within the cell. So everything from gene regulation to metabolism and signaling, etc. And so we're looking at expanding on the range of processes that we can use bond graphs to model to make these kinds of whole cell models. And at least initially, we'll be focusing on bacterial systems, which might be useful for biotechnology. So Joshua Forrest here at Melbourne's is working on this. We're also looking at making a model of the virtual heart cells. So the heart cell combines electrical, chemical, and mechanical processes. So bond graphs, since they're inherently a generic representation, are well suited for this kind of multi-physical system. And so all of this is leading towards a way of making models more reusable. So what we're trying to do is we're trying to introduce some software development paradigms into modeling. The idea behind this is that if you want to work with a model, ideally there's some sort of public repository that you can import the model from. So ideally you'll be able to import the model like you would as a Python package, and then there should be some functions available that'll allow you to, for example, couple those models together in an automated way. And then if you want to update these kinds of models later on, what we're thinking is going to happen is that model's going to be updated in your code. So you've imported an existing model, then you write some code to update that model. So if you put that back into the public repository, you can see where that model's come from and how you've actually updated it. So it might be good as a way of recording model provenance. Okay, so to conclude, we've introduced a BondGraph tools, which is a Python package for BondGraph modeling, and it's designed with automation and extensibility in mind. And hopefully I've tried to convince you that this kind of automation can be useful for certain tasks when we're trying to model biological systems, which can be quite complex and have lots of repeating structures. So that's it for the talk. Here are some acknowledgements for people who've contributed to the development of this tool. I won't go into all of them because there's probably not much time, but I'm happy to take questions.
Thanks, Michael. Do you have questions? No. When you look at those using the BondGraph tools to make that, so the multi-state type models where you can add sort of any other number of states.
Oh, right. Any number. Yeah.
Yeah, so I guess you kind of started going in that direction at the end where you talk about sharing the module itself. But would you look at how the difference between sharing this piece of code versus sharing the generated bond graph? Does that make sense?
Yeah, I'm actually not I'm actually not sure how you'd share a function. I think the idea is you have a specific model. So you've actually called on this function, right? And then once you've done that, you have actually the bond graph as a Python object, and that's shareable. And then you can actually draw the actual bond graph of it. So you have an explicit representation of the model itself once you've called on the function. The function itself is I'm actually a bit less sure about how you'd share that.
Any other questions?
I have a question, Andre. I had to raise my hand, but you ignored me. So, Michael, this is fantastic work. Is the intention to represent the models as Python code, or are you intending to have a sort of a marked up version that would allow other packages, for instance, or other packages that are developed by other people in different languages to essentially exchange the information in a language agnostic form?
Yeah, okay, yeah, that's actually a good point. So at the moment, it's really just Python code, and then the model itself is a Python object that you can copy across. So one thing we are working on, well, not quite yet, but we'd like to really work on in the future is making this toolkit interoperable with existing modeling languages. So ideally, we want to be able to import a bond graph model into CellML, right? And then that can be used for OpenCore later on, and similarly with SBML, but we just haven't gotten to that yet. But it is something we're looking into.
Cool, thanks.
So yeah, I think that's also something you will touch on in the next presentation. And then also some of the things you guys been looking at with the model composition. Is anyone else online waving their hands so I can't see? Shout out if you like. Questions? No? Excellent. Okay, well, thanks, Michael. That was useful.
Thank you.
Years online. Yes, sweet. So this time we're going to try, for those online, you probably can't tell, but we're not very well set up for sound in this room. So we're going to try something different this time to see if it works. But it means that we get the laptop that's connected to the microphone and the laptop connected to the speaker out of sync. So we've got to carefully mute and unmute different things at the right time, or it's all going to go crazy. So if you can't hear from us in the room, it's because we're muting it to save the sound. So we'll give it a go and see what happens. But here, if you want to set up and share your screen, it should be good to go. Here's going to talk about the Graphical Editor plugin for OpenCore.
Hi, Andre. Can you hear me? Thanks.
Okay, are you muted? Okay.
Wait. Can you see my screen?
I've lost the mouse. Sorry.
to that one.
Sorry, not really working. Okay. Try that again.
Can you see my screen? Can you hear me? Hello.
Is that better?
Hello. Okay, great. Thanks. Thanks, Andre. And thanks to the organizers for the opportunity. So, and again, thanks to Michael for his excellent presentation. And I think he laid the, or he did quite a bit of work that I would have had to carry on. So the idea of today's presentation is to actually solicit input on key requirements and desirable features that this community would expect on a plugin that's part of OpenCore that will allow people to create, edit, and simulate bond graphs. So as Michael pointed out in his presentation, for those who have been working on bond graphs, you wouldn't come across a lot of tools that is firstly accessible or is open or extensible that's easily available. So when bond graph tools came out, that made a big difference. And while having a programmatic library is useful, for many of us, a greater appeal of bond graphs is the whole graphical way of composing things and viewing how things interact. So we thought it's good to have a tool through which you could graphically compose, edit, and simulate bond graphs. So there are a bunch of proposals that I want to put forward and get your feedback on this tool that we have in mind. The first one is to create a C++ based library to create, load, and modify bond graphs. Obviously, bond graph tools already provides this, but if you look closely at bond graph tools, it's a Python and a Julia based library. We did think about the option of trying to integrate bond graph tools with OpenCore, and through that integration, pull in much of the functionality that bond graph tools already provides. But in terms of the future directions of OpenCore, the plan is to transition from providing the inbuilt Python environment. So if we have to provide a mechanism to or an environment to create bond graphs, we would have to develop a pure C++ based library so that we can just rely on the C++ runtime environment and not expect OpenCore to provide other environments like Python or Julia to do the job. The idea again is having the ability to create, edit, and modify bond graphs through a library means that we could have users use the library outside of OpenCore, just like how Michael said, you could programmatically access things, you can programmatically create models, but at the same time, through the OpenCore interface, you could do the job using a graphical interface. The key thing is that this library would not be solving bond graph problems. It would serialize a flattened model into CellML and expect OpenCore to simulate the CellML and render the results of the CellML model. So essentially, we would be leveraging the existing capabilities of OpenCore to simulate and render CellML models rather than providing that facility. In terms of serialization, there does not exist any there's no consensus on a serialization format when it comes to bond graphs. There are a range of formats that are being used by people within the institute. They go from text files. I've come across a package that Peter Gosthorpe has developed, which uses SVG, and obviously bond graph tools relies on Python code itself. So for the initial iteration, we thought we'll go with JSON because it's flexible, it's human readable, and also machine readable. Obviously, we don't expect users to edit these files, but access them through the bond graph library. But for those who are brave enough, and often some of us think we are, having it in JSON means it allows us to actually get our hands dirty. So in terms of the graphical editor, this would be a plugin that will be provided as a part of GUI of OpenCore. And the key features that this plugin would provide is firstly able to create a bond graph, edit bond graphs that somebody's created already or that you have created. And from these bond graphs, create a flattened CellML model using the library that has been developed. And that's purely based on C++. So the key thing that the graphical editor would do is hide the API and the software signatures from domain experts and modelers. So if somebody doesn't want to deal with the programming side of things, obviously, because it's a completely GUI-based environment, the whole thing is transparent to them. And obviously, providing a seamless experience for developing the models, translating them to CellML, and simulating it in OpenCore. So the way we envisage this plugin is it would look something like this. You would create a new model or open a model, bond graph model to OpenCore, and then based on the MIME type, it will open the plugin, and then you would see a particular view through which you can drag and drop the standard bond graph elements. We will have reactions in them. And then you would be able to compose a bond graph by dragging and dropping these elements and then creating the bonds through which they exchange energy. In addition to that, you will have another view through which you can provide inputs. For instance, what are my initial values? I'm also thinking of providing a way through which you could provide meta information like any notes or annotation stuff. Obviously, the way we've thought about this, you will be in one mode, you can drag and drop these elements, and that's and in another mode, you would be able to actually draw the bond relations between these elements. You'll be provided standard GUI features to zoom in, to pan, and all that stuff. And the other key thing would be is you'll be provided with certain geometric annotation mechanisms. So for instance, you could probably draw a particular or highlight a specific region within your bond graph and say, these elements are related to a particular physical process or something like that. So there'll be some such elements to it. So this is the initial mock-up that we have in mind. And the one additional thing that we want to add to this user interface is how we could compose large models. So one thing when you start building large models in a completely GUI-based environment is it could very easily get very clumsy because of the large number of elements that are there and the large number of bonds and relationships that we would start creating. So in order to handle this and also to enable modular development, we are thinking of bringing in this idea of composite elements. So composite element is you can think of it as an abstraction that you would drag and drop into your canvas, and then you would import an existing bond graph into that composite element and only expose certain elements and junctions within that particular bond graph that you imported. And these sources and junctions would then be exposed in the canvas in which you're composing the current bond graph. And that will allow you to connect with the other elements within the current canvas. So that way, you reduce the amount of clutter that you see in the canvas, and it allows you to bring in many different models, and also allows you to test these models independent of the large model that you're developing. The composite element will also allow you to manage the parameter and state variable names. So for instance, if you are bringing in a model that solves the metabolic profile of a particular cell, and you want to see how two different cells are interacting, the things that would be changing in this model would be your parameters and the parameter values. So the composite element would then allow you to actually go and change just those parameter values. And it would, in a sense, automate the name clashes that might occur if you're having two models or two instances of the same model. I just talked about the graphical annotation a bit earlier. So these would be just standard graphical shapes, geometric shapes, which you can drag and drop into your canvas, change their size, and highlight regions within your model so that it kind of gives some cues for the modeler. So we will also try and support user preferences. Say, for instance, some people prefer using the half bond arrows. Some others would prefer to have the full bond arrow styles. So through user preferences, you could select what kind of arrow styles you want to render. There's proposal to color the flow and effort variables, and you could go and choose these colors. And obviously, for a novice user, it would be always good to have prompts which say whether you want to remove certain things or whether you want to change certain things. And these could get quite annoying once you become an expert. So again, enabling and disabling confirmation dialogues, that would be a part of your user preferences. So in terms of the development cycle, what we're planning is to release, to provide an initial release with the proposed features, which is the library, the GUI that I discussed earlier, and then start to solicit feature requests for the GUI through the open core repository, and solicit feature requests for the bond graph library through a separate repository, and then coordinate the feature development and plugin releases with the open core releases. So there are a few items where I thought we could have a little bit of a discussion. The first one is in terms of flattening an imported bond graph model. So if, again, going back to the example wherein we wanted to say simulate or consider a particular scenario where we want to simulate multiple cells that are going to interact. And the differences between these cells would be just in terms of, say, parameters for these of this particular scenario. So we have one bond graph model that, say, models the metabolic profile of a cell. And then we imported 4 or 5 of these cells that may, say, represent what's happening within, say, the gut. And we want to see how the interaction, or we want to simulate this particular interaction. So at the first level, we would be importing let's say four different bond graph models, and then connecting them. We could then start imagining that once we go from, say, one organ that's composed of four bond graph models, we can start thinking of more than one organ and how these organs interact, in which case we'll have another hierarchy of bond graph models coming in. So thinking of how do we flatten these? Do we flatten them at the level of the GUI so that when the GUI creates the CellML is already flattened? Or do we create four components within CellML and expect the CellML, expect OpenCore or CellML libraries to deal with that? So that's one part. The second one is in terms of exporting bond graphs. Obviously, we can provide features for the user to print them as PNGs or JPEGs for their presentations and publications. We could also support the export of bond graphs as SVGs, aligned with what Peter Gothrop's SVG tools does. The next one is in terms of user preferences. Do we provide user preferences or workspace preferences? So when I say workspace, you can think of a workspace as a sandbox or an abstraction where you create one for a particular project, and you can provide certain features and preferences that are specific to that particular project, which is different from the user preference, which you can think is universal across the different projects that you're working on. So which would be the most preferred way to go in terms of providing preferences? And finally, in terms of model provenance. So CellML has a way through which we can capture the provenance, but because in bond graphs, we are capturing graphical annotation and graphical information. Currently, the idea that I have is to catch this provenance information in the JSON file. Is there another way through which we could capture this or record this for models, and in terms of sharing these in PMR? So I thought maybe inputs from the community on these 4 points would be quite useful. Andre, would you mind coordinating?
Cool. Did you unmute? See if this works. Cool. Thanks, Jigger. Yeah. Sorry. Okay. We're tweaking the sound as we go. But thanks for that, Jigger. I think that was useful. Can I just clarify that development cycle? Is that proposed or there has been an initial release? That's the first step.
This is the proposed one. There's nothing been released yet.
Oh, now we can't hear Jigger.
Sorry.
Okay. Sorry, Jigger, we couldn't hear you.
How about now?
Yep.
So this has been proposed. There's nothing been done or nothing been released.
Yeah. Cool. Okay. Now we got echo. There's someone else has a microphone. I'm muted. Oh well. Dave. Oh. Who's got their microphone on? Who's got sound? Okay.
My own comment on it in terms of export. Export is not use one of the graphic advanced standards as export. Export as a set of edges and nodes, and then refresh to bring that SVG or PNG or whatever.
Sorry, Andre, I couldn't hear that. Would you mind repeating it for us?
Put a microphone on.
I don't keep it through our speakers.
Can you hear me there? Can you hear me there? Just a comment on opposed to using an export format. I would suggest that instead of using SVG, to use a one language or formats. Dot is a very low level common one, which allows Raft as a graph instead of vertices and edges. And then use other tools to read that graph as SVG or SVG or whatever else rather than going straight to SVG.
Sorry, Dave. Sorry, Andre. I think I wasn't able to hear David. There's too much echo. Would it be okay if David could tell it to Andre and Andre could just speak it through a single microphone?
Yeah.
Yeah.
He's trying to work out where the echo is coming from.
I'm going to turn the speakers off.
Working.
I'm joking.
Okay, sure. Try that.
Try that.
Try that now.
Is the microphone?
Is that microphone? Third time. I was going to say, instead of exporting the bond graph as an SVG, to export it using a format for graphs, as export it as a set of nodes and edges, and then let other tools render that as SVG or PNG. For instance, the dot notation is one graph export format.
Yeah, we're here.
See the chat message.
Yeah.
I've got sound on, for sure.
Sorry, if you're speaking to you, we can't hear you.
Oh no, I was just I saw Dave's comment in the chat, so I just said thanks, Dave.
Yeah, so do we, I mean, so the work Peter Gothrop was doing with the SVG and bond graph tools, do we know how far advanced that is? Is that usable as is?
So the thing with the SVG serialization that Peter Gothrop have developed is it only captures the connectivity information. It does not capture things like the parameter values that each of the elements should have. And I think that is one drawback. We did think about annotating the SVG format and adding this through a separate XML namespace. But I think, there's really no value that we get by going down that route, because if we have a library and then if we provide a format through which we can serialize the bond graphs that are being created, we can always write the logic to translate that to any particular format that's needed, like the SVG one. I mean, unless we come up with a consensus on saying that this is the best way to store bond graphs, which I don't think we are or we have at the moment. we've decided to go with JSON for now.
You should be able to.
It's just tricky. You probably can't hear me, but I put it in the chat. I just think it's important that we preserve parameter sets, the provenance of parameters separate from models, because it'll often be the case that a model captures the structure, but the particular instance needs to be captured through parameter sets that are important. So that the bigger issue with provenance is the parameter sets.
It's exactly what we did first. That's exactly what we did first. The gradient parameters. Yes. Did you want to bring up those discussion points again? You did. So maybe if we start with the first one in terms of flattening. Does anyone other than Andre have a view on how this should work? Oh, I'm just going to this one.
We have to do that what we are currently doing with slips and I think the issue of the flattening of one graph is when we want to basically go from one graph to a CellML representation. And starting with the bond graph may import other bond graphs. The question is whether we need to flatten everything before starting CellML and have that flattening done automatically or not. And in CellML, for instance, when we want to generate code, we have something similar in some ways, which is that we start with a CellML file, which may import other CellML files. But if we say, okay, generate code for that CellML file, then we don't take into account the fact that CellML file may import other things. If you want to generate code for the whole thing, it's the CellML file and all the imported bits, then the end user will not say, okay, flatten my model, then generate code. So in a similar way to what we are currently doing for this CellML, I imagine that we should do something similar here, which is that if you have a bond graph that imports all the same, then it's up to the end user to say, okay, first flatten my bond graph, then convert my bond graph to CellML or whatever, as opposed to need one graph. So the library that the checker was talking about. So what I don't think we should have is that the library shouldn't automatically flatten your model for you. It should be the end user's decision to say, okay, I want my model to be flattened. I mean, because there may be different reasons why you want to flatten or not, and then export to CellML and whatever. But no, I would imagine that's probably what they think, because I think that's what we have done for this CellML. But who knows? There's to change it.
I agree. It's the user's decision when they're offset.
So I think, I mean, that's the thing. That's what I told Jerry offline. Actually, what I just described is what I would expect for the library itself, so lead on that. When it comes to the GUI like OpenCore for me would be the end user of the library. So OpenCore, you might using OpenCore say that OpenCore will automatically flatten your model. As I said, OpenCore is going to be the end user of the library. Having said that, maybe even with OpenCore, we could have a parameter user preference that says, yeah, I always want to flatten, or no, I want to decide myself, the end user of OpenCore. I want to decide whether I want to flatten something. That's where I come to the JS third part user preference.
Okay, so I think that answers that. Did you get it? Is that right? So the supporting SVG, I think we talked about that before. There's a number of export formats.
mean, it's one thing to keep in mind is that with the SVG export, so what we currently have in mind is to create a plugin for the core, for the GUI, the graphical annotation of the Polygraph. Now, if we think that OpenCore we can use the Qt framework when it comes to graphics, etc., allows you to usually export to different formats automatically. So we could potentially have an export to SVG, PNG, whatever format. Yeah. But also, when it comes to the live graph steps of the library, you have a way to export the bone graph, which is encoded into different formats, which you mentioned, and for the library, in order to export from bone graph to whatever format, such as FTG format.
Yeah, I mean, I think that oops. I mean, I think essentially what we're saying is there's many different ways you might want to export. The important bit is to make sure that we keep, the semantics. So yes, is what we want to make sure we keep, and how we do that exactly. Whether it's the Python modules with some sort of JSON description, Python is CellML, so Encoding CellML, export everything to CellML. There's many different levels of the export. But I think the important thing is you need to be able to collaborate and archive the semantic description of the bond graph model in a way that's clearly linked to parameters. I think we can describe parameters in CellML very well. We can describe math in CellML very well, but it's obviously not the best for the bond graph structure itself. I think there's probably still work to be done to see how we do that, particularly as we look at provenance. There's a lot of effort across combine in terms of provenance and how we should store that and use that, both in combined models and more generally the data and look at the data. That's a real interesting debate.
What is in that proposal that becomes semantically for bond graphs? What is the, I mean, in the end, you've got to have one or multiple, but one single reference source for any model, right? So what is the single reference source that you regard as the underlying truth?
And that's the interesting bit. So if you can hear Peter's question is, what is that single source? What is the truth for a bond graph model? And I think it's not, well, my view at this point in time is it's not one thing. There's many things. There's the bond graph network itself, and the connectivity. There's the parameterization for any given instance of a simulation you want to perform. There's the particular equations that you need to go into it, which some of them are generated or generatable given a bond graph, but others are not. And on top of all of that, there's the more interesting part of it is how to make it usable by people who are not us. To encourage people to use best practice. I know we had a big discussion with Edwin the other day, just throw him under the bus, about how we can start, are we at a point where we can move away from talking about bond graphs, and it is the best practice and the tools help. But at least to me, it's not really clear what that single source is. I think it's a collection of things.
Trying to go back to the microphone we can hear each other.
I think we can hear if he's talking maybe. I'm hoping some of that might have come through to you.
I could get some of those, but it's good that Alan is there. So I'll probably sit down with him on Wednesday and get more of what was decided.
Sounds good. Okay, so for workspace versus user preferences, the other idea or another way to think of that is standardized versus ad hoc. And is there a need for a user choosing how they look at things, or do we want to standardize on what a bond graph is so that anyone looking at a particular model knows what it means in the same sort of way as an electrical circuit diagram, or where the system biology people with SPGN are going. And also, bringing in the point of making these things accessible to normal users. And I think this is a huge area. Is that you can have harpoons versus arrows, colors and no colors. Many other things. I don't know if others have thoughts. Of course, about his thoughts. Maybe come and speak at this microphone. Then we'll see. Or go speak at the camera. But then anyone definitely hears. Elon's just going to go off behind the camera and see if he can hear it.
So I think, for the preferences, for me, it would be at the GUI level. And if I'm thinking of the way OpenCore currently handles user web preferences, it's definitely at the user level as opposed to the workspace level. And David was mentioning the kind of standard versus ad hoc preferences. And clearly the format that we would be using for encoding the network itself, the bond graph network, that would, once you open that in OpenCore, say, by default, it would be using the standard way of representing that network. But then it would be completely up to the user to decide, okay, actually, no, I prefer the full arrows as opposed to half arrows or whatever. And I think that's completely fine. At the end of the day, it's like a text editor. Nowadays, you can decide to have a color coding for anything. And it's up to the user to decide, okay, I want to use that color coding set or that one or whatever. So in that way, when it comes to representing graphically a bond graph, you could have the default profile, which is the standard way of representing a bond graph. And then if the user wants, then he can change that. But I would still do that at the user level as opposed to workspace level, which I understand JK means kind of for a particular modeling study, you want maybe to be able to say, okay, I want to use these settings. For another modeling study, you want to use another set of settings. And I think that would be overdoing it maybe. So I would just stick to user preferences, which is at the kind of software level, so to speak.
Thanks, Alan. That was very clear.
Everyone get it. Yeah, I think the only, because then you end up with many people with many different looking bond graphs. You want to publish or share the model, you start getting different people talking about different things when they mean the same thing.
When it comes to publishing, I would expect people to use a standard bond graph representation. At least that's something that would make sense to everybody. I would expect everybody to know that standard and that's it. It's just that to make people's workflow as easy as possible. Then, yeah, they may want to use this representation or that representation because that's what makes them more productive, and that's fair enough. But when it comes to publishing, yeah, just use the standard representation so that way at least everybody is on the same page.
Okay, any other comments from anyone? So maybe just to talk a bit about model provenance, and we'll go through a bit more of this in some of the later talks. In combining, which we'll use later as well, this effort to try and consistently do things across the different modeling standards. There's this idea of having an archive as a sort of export of a piece of work. And in that archive, you contain everything about that piece of work. And for that, we have an evolving or a revisioning metadata standard for how to describe the knowledge about that piece of work as a whole. And that includes very high level provenance information. Mostly about the model as a whole, but a little bit getting into some idea of being able to link, particular data sources with where they came from and things like that. So it's definitely something to keep an eye on. Some of us are obviously involved in that, and I would hope that anything else we do builds on that approach rather than coming up with something new. And that approach, we're pushing hard to move SPML away from their sort of hard-coded RDF-ish looking XML to the actual RDF, which Dan certainly serialized in various JSON formats as well as other formats. I don't think there's any issue with anything in this proposed approach. We should just make sure we keep these things linked together. It's a whole bunch of people working on provenance in all sorts of places. It'd be good not to duplicate. Then I others. Okay, just not so you have to do this. But yeah, and essentially that's the level of interoperability of what's happening in DMR as well. Is we'll be following the sort of combined efforts in terms of provenance and other types of annotation, as well as more and more as we link with other projects in terms of data.
I think my expectation would be that for every model, you have at least 10 different parameters. Because, so often advantaging the same structures and views. What you care about is the way the parameters change.
Yeah. So if you couldn't hear Peter, he was just mentioning about how for each model you're likely to have, on the order of at least 10 different parameterizations. And I would think you're going to find a lot more. And you're also going to find parameterization that sits outside the piece of work, so you're just reusing that model from the local tree. Setting your own parameters.
Yeah. So thinking about the work that JG is about to start, and I think for me the very first step is to agree on the format that we are going to use. So from what I understand, it's still kind of an ongoing debate as what is the best way to go about encoding a bond graph and only encoding the interactions, etc. And then to have the parameters as a potentially separate file or whatever. So clearly, we need to do some work on that before JG can do anything with lib bond graph itself. I mean, that's fine. That format is at the root of everything. So,
which format, sorry?
The format for encoding bond graphs, etc. I mean, we need to know exactly how are we going to solve the problem. Because initially, I mean, what JG has suggested is to have that JSON format. And my understanding, I mean, Jagger to correct me if needed, but my understanding is that that JSON format that Jagger has in mind would contain everything. Yeah, I mean, the description of the bond graph itself, as well as the parameter values. Now, from what has been said today, I understand that we want potentially the JSON format to contain only the description of the model itself, and then the parameter values to come from outside. But how do we handle that? The fact that the model parameter, the parameter values come from outside. Is that something that is done within OpenCore itself, or is that something that we can also do within libbondgraph? Or I don't know. I mean, that's basically, I still have coming here today, I have more questions now than I had before, but that's fine. I mean,
so luckily, you know, I don't think she'll talk about it, but even if I solve that problem for Python bond graphs using annotations, so we can, I think.
I mean, do we really want to keep using annotations? I mean, annotation is for me, for other different modeling projects, I mean, I found annotation to be useful to kind of get the ball rolling. For me, that's a nice way of getting the ball rolling. But I think at some point you need to kind of standardize things as much as possible. Otherwise, it's not going to be easily portable. I mean,
exactly, and that's why it is standardized, so that you can, in a standard way, using the metadata, say this particular thing is concentration of some solution. And then if you describe something in your bond graph as that, you describe something in a CellML model as that, then software can work out those are the same thing.
Sure.
So yes, it depends on using standardized annotations to describe the biology. And I think potentially to do the full system then needs further standardization on how to describe bond graphs beyond the biology.
Yep.
Or maybe the biology is enough. See. Okay. Any other thoughts or questions? I think we'll next have Niluka talking a bit about her project, and that will probably lead to further discussion on very similar issues.
Thanks, Andre. Thanks for coordinating. That was quite useful.
Good, good, and we'll definitely be following up a lot. I think. Cool. Okay, so we'll move on. Still nicely on time. So now, I don't know, did you want to use your laptop? Or just, yeah. So we'll try a different computer to the current computer. Yes. Yes, we should share your screen. And that impression we just plugged in.
I'm Nifa, and today I'm doing a first introduction to my project. It's about automating model composition. So here we all know about PMR, the physio model repository, which stores physiological and anatomical models in XML format. As far as I know, there are over 800 workspaces, including computational models, which are stored to be accessible to everyone and are meant to be reused. PMR ensures that models are fair, findable, accessible, interoperable, and reusable. So we want to reuse and compose models. But is it always straightforward? Can we always make it work? So we know that models on PMR are in the same language, but not necessarily in the same modeling framework. And here comes the challenge. So one solution is converting all the models into one particular framework. And if you ask which framework, we believe that bond graphs meet our expectations. You can easily attach or detach models to it as modules, or you can simply delete or append sections of the model, because bond graphs are inherently hierarchical. But we want more from our composition procedure. We want it to be automated. So let's say we have our modules in bond graphs, and we want to automate the procedure. But if we automate it, do we definitely get our desired final model? So here is an example. You can see all these puzzle pieces seem to be in the right place in terms of their structure, but the final figure shows something implausible. If we annotate our models, which means giving a standard and meaningful labels to the variables, we can easily compose them with more confidence into the output. So finally, we want to facilitate model composition from cell level to organ and from organ to whole breath. And that's it.
Thank you. Do you have any questions? Is it all nice and clear? Annotate your models and put puzzles together. Yeah. Thanks to the camera. Oh.
Thanks, Niloufar. So when we talk about the standard framework, do we need to follow the standard framework to use the same annotation, or are you working on some platform that automatically can convert any type of model to that standard framework?
So ideally, it should be what you're saying, but for now, we just have some bond graph templates for each type of model. I mean, for a list of models that we're working on. So now we have symbolic bond graph templates for some models working on it. But yeah, ideally we need a system of platform that automatically converts any model in, for example, CellML into bond graph. But right now we don't have that.
Okay. So where are you at in terms of, I mean, if you had two separate models properly annotated, but you haven't gone to the process, through the process of doing all the linking that CellML requires to couple those two models, what level of automation have you managed to achieve in terms of automated linking between two previously disconnected but properly annotated models?
So now, as I said, for example, we have two different CellML models which are annotated. We have two different CellML models which are annotated. And what have at the moment is that we have template Polygraph models of those CellML models. Then our function extracts those annotations from the CellML models, and based on those annotations, it puts the parameters or any value that it gets from the CellML file into those symbolic Polygraph templates. So then, by matching the annotations and finding similarities between the annotation, it just couples those models together by adding bonds between the Polygraph templates.
That's working.
Yeah.
Cool, thank you. Okay, so we still have a few minutes before our lunch break. Is there anything else anyone wants to talk about how to make the world use bond graphs without knowing that we use bond graphs?
Maybe a question from Melbourne. Have they started looking at Polygraph tables? Because when we see bond graphs as being a zero-D version of a more general environment, which has huge advantages in terms of making PDEs into the same framework. Is anyone in the Melbourne team looking at these issues?
So I don't know, Michael, Edmund, maybe if you heard Peter's comment about whether you guys are looking into four Hamiltonians, is this a more general version of this zero-dimensional bond graph? Anyone said that?
I can talk a bit about this. So I guess the short answer is not quite. It's something we're interested in, but it's just yeah, it's, as Edmund says, it's just we're just have our hands full a bit.
So as Michael was saying, they're very interested, they're very busy on things, but haven't done a lot. There's something upwards. What else? Okay, well, we might call that a morning. Okay. Okay, well, thanks everyone. And we will break for lunch for just over an hour. And we will try and improve sound during our lunch break. And not get any feedback. Thanks to everyone online for joining us this morning. It's been very useful. We'll be back at 1:30 local New Zealand Standard Time with some number of lightning talks. Again, anyone wanting to volunteer additional lightning talk, feel free. Or just randomly pull people out of the audience. So, thank you. Enjoy lunch. I think it's up at the restaurant, which is somewhere over there. Sure, we'll find it. Cool.